Trinity Maths, Pythagoras Theorem. This is our destination. How do we get there? Close the Excel file. From Trinity Maths, select Geometry, open Pythagoras Theorem. This is a macros-enabled Excel spreadsheet, and I'm looking for find main diagonal D of a cuboid given length L, width W and height H. This is an interactive diagram. I have dynamic control of the cuboid's length L, width W and height H, which I can increase or decrease. All three dimensions can be changed simultaneously or hidden if I wish. The background replicates isometric dotty paper. This can be presented as isometric grid lines or a plain background, but I prefer dotty paper. We were given starting conditions, but I'm going to create a new cuboid with L equals 5, W equals 6, and H equals 7. You might get your pupils to draw the cuboid on printed dotty paper, which you can download from the Trinity Maths website. Ask your pupils, can you find the length of the cuboid's main diagonal D by algebraic methods? Pythagoras in 3D is very similar to Pythagoras in 2D. Sub in the known values of 5, 6, and 7. Evaluate the square of each dimension. Then add all three values. Finally, find the square root of both sides. We reach for our calculators, and here's our answer to 9 decimal places, which gives the value D equals 10.5. Don't forget the units and state the degree of accuracy. Now this is all very procedural, developing our pupils' fluency, but how can I introduce an element of reasoning or problem solving, or perhaps conduct a mathematical investigation using this activity? Let's reset the screen, but reveal the answer and ask our pupils, are there any cuboids with integer dimensions where its main diagonal D is also an integer? This may be similar to an investigation you may have done with your pupils to find Pythagorean triples in right-angled triangles. By exploring the 3 dimensions of this interactive diagram, I found one such cuboid. When L equals 3, W equals 4, and H equals 12, the main diagonal D equals 13. Let's check this by performing the procedural calculation once again. This checks out. Therefore, 3, 4, 12, 13 is a primitive Pythagorean quadruple. Your pupils could use the Trinity Maths program to find more, or alternatively explore this relationship between the 3 dimensions using written methods. Even on the small isometric grid shown on screen, there are 6 more primitive Pythagorean quadruples waiting to be found and drawn, and there are obviously many more beyond.